Rightio, another year, another SYS2. So sticking with Raspberry Pis, because I think that gives people an opportunity to build their own servers at home, so it makes it very accessible. But the ones I built last year are a little bit flimsy, a little bit prone to damage. They sat on my windowsill and they kept getting knocked off when the wind blew the blinds. So this year I've moved them into some metal cases to make them a little bit more rugged. And that's what we have here, and I must admit my first impression was deep thought. I don't know, yeah, see the likeness? But basically they're made up of 3 thin client cases. So I found these in our e-waste bins. So these were going to be recycled. So they had these nice metal cases with built-in power supply and fans. They came with an old Intel Atom-based board. I did think about using these, but they're so old that their mass storage interface was IDE. So yeah, makes them a little bit hard to maintain. They did have USB, so I could have put a USB drive on there. But yeah, I decided I'd use the cases and the power supply, but I replaced the guts with some Raspberry Pis. So we ended up with this. So in the same case, so I used the 12 volt power supply, so you had 12 volts coming in, and then it's passed through some switch mode power supplies to give us our 5 volts that we're using for our Raspberry Pis, and the 12 volts that I'm using to control the fans. So yeah, that makes a very nice compact box for our various lab servers. So basically the same configuration, just packaged up in a little bit more of a robust case. So here's our new lab server. It's actually quite heavy. The bottom switch weighs a ton. But if I give it a quick rotate round, you can see we've got the side vents there with the fans on the back. We've got our 3 cases. And each case has 2 Ethernet sockets on the back that feed through to our front patch panel. That connect to the bottom switch. On the top you can see we've got an I2C LED display. And this time I'm using a cheaper USB-based GPS receiver. It works really well. It's on a ridiculously long USB extension cable. The only small if button maybe is that our UV screening on our windows blocks the signal, so I have to dangle it out the window. So you can see the basic construction here. So we've got the 3 cases stacked on top of each other. I've got 3D printed spacers. The hard bit there was not to block the fan intake vents, and I'm using 4mm studding to kind of clamp them all together. So yeah, it's actually quite robust. It's a little bit wobbly, but a lot better than the ones I have on the windowsill. Again, you can see on the back here, we have our Ethernet cables coming out the back. So 2 sockets per box for our various servers. And another nice thing about these cases is that they allow chaining of our 12 volt power supplies. So the power comes in on the bottom box, and you can see we've got 2 leads chaining the 12 volts from one box to the next to distribute that power between our 3 cases. And we've got some expansion holes at the back there, so you can see we've got the I2C cable coming out of the bottom box to the display on the top. So this new server rack gives us 6 Raspberry Pis, implementing our various lab servers. So we've got our NTP server, DNS server, FTP server, SMTP server, Docker server, and IRC server. These all connect down via the patch panel to the bottom switch. Again, high quality e-waste here. That's an old 100 megabit switch, which connects to the lab's network. And as always, this server's running in my office, just so I can quickly give it a kick if it breaks. If you would like to build your own version of these servers, all the instructions will be on my website. I know some of it is specific to the film clients I've used, but all the build details are there, so hopefully there's something useful if you would like to build your own NTP or mail server running on a Raspberry Pi. So yep, please do have a look. The link will be in the video description. As always, another year means recloning the whole lab again, just to make sure all the Raspberry Pi base nodes are up to scratch, and making a few modifications to their installs to support the various labs that we'll be doing this year. So what I like to do is to power them up all at the same time and connect them to the lab's network. That's the only way to test them, to make sure that they're all functional. As always, testing has to replicate the environment they will be used in. So when they're all connected to network, I've got some scripts that test that the Pis are active and that they're being configured correctly, just to make sure no old SD cards have slipped through and they're running last year's image. Okay then, so we have approximately 80 desks in the lab. Each base node, as you can see here, has 3 Raspberry Pis in it, so we have 240 Raspberry Pis. And yes, it does take a long time to reclone 240 SD cards, but I have a rig set up in my office, so I can do those in parallel. So, with all these Raspberry Pis connected to the network, we have a cluster of effectively 240 nodes. And each Raspberry Pi has 4 processor cores, so in effect we have 960 processing elements. So this opens up the possibility of some parallel processing. So can we use these Raspberry Pis to do some serious number crunching? And I'm guessing the answer is probably no, because the bottleneck here is going to be the lab's network. The Raspberry Pi's local node switch, so that's a 100 megabit switch. So yes, the Raspberry Pis can do gigabit, the lab's network switch is gigabit, but to connect to the lab network, they have to go through that 100 megabit switch. So that's a bit of a bottleneck. But it does depend on the application you're running, so there may be possibilities. In the past, when I have done some parallel programming, I've used the MPI library, but to keep things more generic, I thought we'd program this one from basics. So what we got here is this setup. So we've got our PC connected to the lab switch, and then we're going to connect to our cluster of Raspberry Pis and see if we can program them to do something. So our challenge, if we're not going to use MPI, is how do we distribute that code across our worker nodes? How do we then run that code, and how do we get results back to this case here, our PC, so we can see some results? And we're going to do that just with some simple bash scripts and some Python. So the first thing I wanted to write, just to create that framework, was to develop a system where you had a head node and some worker nodes. Each worker node, the Raspberry Pis, would send back their core temperature and their IP address, and that would be displayed on the screen as you can see in this mock-up. So each square is a Raspberry Pi. You can see its temperature, and the colour would represent how hot or cold it was, varying from a typical running temperature on a Pi around about 40 degrees up to kind of 70-ish if it's running hot. So yeah, I know there's no parallel processing here at the moment, but just to create that framework, just to get things started. So here we have version 1 of our temperature plotting software, and you can see each of the squares there, and if you pay attention, they do change occasionally as the temperature fluctuates in the lab. So you can see there's some hot there running, the yellow ones are running at 60 degree, the bluish coloured ones are running in the 40s, greens are in the 50s. So yeah, you can kind of see them changing as those packets are sent by the worker nodes, received by the head node, in this case it's an old laptop, and they're plugged on the screen displaying their colour codes. I can zoom in a little bit, but apologies for the fuzziness of the video recording. It was done on my phone. If we look closely, again, we can see the various temperatures changing each time the worker node sends an updated temperature. As always, if you'd like some more information about this implementation, you can find that on my website. So on this webpage we have our worker code, the Python code that sends our head node its temperature and its IP address so it can be plotted on the screen. The head node's IP address is fixed, so each worker node opens up a socket to this IP address and this port and sends its data to the head node every 2 seconds or so. Each worker node is specified in this text file, so the IP address of the worker node that needs to be sent the code and told to run this code is defined just as a simple list, a simple text file. And then I use this bash script here to send that file to the worker node and tell it to run it. So this part of the script here sends the file using SCP. If that was successful, we use SSH, then tells the Pi to run that program to send that data. I do confess these scripts are a little bit fragile, but you can run the script multiple times. Each worker node does test to see if the code is already running on that node. So if it does detect that a version of this program is running, it will exit gracefully so you don't end up with lots of duplicates running on each Raspberry Pi. So in practice this does work fine. You do see some of these scripts getting a little bit confused at times because there's no exception handling, but we can brute force it. When all your worker nodes are up and running, we can run this code on our head node to receive that data and plot it to the screen. So just using tkinter here to plot it to the screen. And yeah, it looks quite pretty, I think, and it shows you the status of each of your Raspberry Pis. When this was done, they weren't running any other code. So yeah, I think the next step is then to get them to do some number crunching and see how those temperatures do vary. So at the moment it's about as far as I've got. So we have now a framework where we can upload our programs and run our programs across our cluster of Pis. So we need to find a problem that we can spread across that cluster, and it seemed appropriate to start off with a classic, so Conway's Game of Life. And that's what I'm working on at the moment. So fingers crossed, touch wood, I'll get that working before the start of term as a nice demo. But I think that's where I'm going to leave the video for now. I will catch you all next time, which will be in September. Or more specifically, September the 22nd at 9 o'clock for our first lecture. Oh, I'm going to have to get used to that. We're moving away from 9:30 starts to 9 o'clocks. Oh, I don't like morning starts. But it'll be all good. It'll be all good. I'll catch you then. Bye for now.